Okay, in last tutorial we have just finished the example 1, which is the rigid connection for the bin and column, and then we have done this one in Autodesk Lobot already. So this is the structure we built in last time, and also we can have a quick look at the results of all the deformations and the member force. So first we have a look at the deformation. So this is a deformation for combined loading, and then if you are interested in to have a look at what is a dead load, so this is dead load deformation. They're pretty small, so if you want to have a quick clear view of it, so we can change this to 5000. So that's give you the view of the vertical settlements due to the vertical loading. And also if you want to have a look at the live load, which is the lateral load in here, that's too big, and then so let's change to this one to 100 the scale. So we should be able to have a pretty good view of what is the deformation for the lateral loading. And if you want, you can have animation of to have a look at the structures, how they deformed that are subject to the lateral loading. And if you're interested, you can see the combination combined load as well. So if you want to stop the animation, just click on this one here. So let's stop this animation and close this part. So after deformation, let's have a look at the member force, the actual force that for the dead load. And so click on actual force and click on this one. So that's the actual force. The actual force accumulate layer by layer and change down to the ground, so they become increasing. They increase gradually from top to bottom. And live load. So this is live load. And I need to maybe disable the deformation and click on apply. So only the actual force will display in here. So this is actual force we have that display in here. If you want to have a better view, say let's maybe create this one, increase this one by 4 times to maybe to 800. So click on apply. Oh no, sorry, that's the other direction. So let's change this one to 100. So maybe 2 times bigger. So this looks like a quite clear view of how the structures is transfer the force from one end to another by the rigid connect bin, and then so they form a rigid frame structures to withstand the lateral loading you apply. Okay, and the moments and is shown in here. So this is the moments you can have. So let's maybe put in this one to 10. Hopefully that give you a better view. Oh, 10 was too big, so let's maybe put in 60 and apply this one. So that's maybe a better view for the lateral load. So when you have a lateral structure, lateral load, and how the bending moment distributes inside the structures. And then this is combined effect. So that you see this is a curve is caused by the uniform distribute load in the middle. So that's what we have done last time. So what we're going to do now, we're going to maybe that convert these structures into a new separate one, in which the structure here we're going to have that pin connection for each bin in here, and also because it's after you put in the pin connection for each bin to column, then this will become unstable structure, and so we need to put a diagonal here to stabilize the structures, and all the diagonal here are pin connection as well to the each corner. So after you set up this one, then you will be able to get another type of structure, which the bin and column here is the vertical system, will take in all the vertical loading and transfer down to the ground. And then the diagonal here and the frame system here will form a tower. This rigid tower is going to take on the lateral loading, so which this system here is called lateral system. So let's come back to Lobot to see how we can do this one. So let's do first thing first, which is going to that assign the pin connection to each one. So to do that, we need to use the structure definitions. So we click on this one to bring up these windows, which is quite useful for us to set up the release for both ends. So let's use the release. So when you click on release, and then we are using the pin connection for each pin. So after we pick up this one, then we come back to the bin. Then you see the cursor is changed to a special one, which means you are putting the release, assigned release to the bin. So let's click on this one. So you see both ends are pinned now. So let's do it one by one. And so that's all finished for this one. So pretty easy, right? And then the second one, we need to put in a diagonal. So let's have a look at what the size of diagonal. So diagonal, as we said, we use a hollow section 168.3 times 5. So let's maybe come back here to draw the diagonals which we have in here. So let's use this function to draw a bar. So this time we use a simple bar, because it's just a tension and compression we have. And then the cross section we have is a circular hollow section. So we use the circular hollow section, and then that's going to be 168.3 times 5. So that will be this one here. And then we click on add. So you see this one has been changed proper one. Let's close this window, we don't need it anymore. Then what we need to do is highlight this window, and then can start to draw the diagonal. So let's do this one by one first, and then we don't need the drag, so we untick the drag, and then we draw the next one, and we draw the next one, and then we draw the next one. Okay, and then so that's the last one here. Okay, once we finish, this is a tower, and then we also need to, and then let's close this one. Let's going to apply the release to it. So that's also the pin connection. So we pick up this one, and this one, and this one. So this one and this one, this one and this one. Okay, so that's all done. So this basically the structure is converted into a new structure with the new pin connection and a diagonal tower. So once finished, then let's just have a quick look at the loading still there. So let's have a look at the loading. So the loading seems fine. So let's have a look at one by one. That's okay. So what we can do now is just continue to run the analysis. Just click on calculation, and then there's no errors. That's great. So let's maybe have a look at the results. So let me bring up the results layout. Let's click on this one and go to result, and then click on this one. So let's have a look at the deformation, and then we can use the first the sand scale to have a look at the lateral one. So the lateral loading, you see the sand scale 100 that we're going to use in here. So if you click on apply, so you see the deformation is much smaller than what we used to have before. So you can see, even though that the diagonal is a bit ugly to the architectural point of view, but however they are quite efficient to withstand the lateral loading. And then have a look at the vertical deformation, and caused by the distribute load. So let's change to 5000 and click on apply. So you see, and due to the tower here, so you get a slightly stronger structure in this side, so you have a less deformation, and then is also unsymmetric deformation as well due to the tower you built up in here. So this is only one drawback you possibly can see, and then also you can see that's the combined effect. Of course, this 5000 is too much, so let's maybe change to 100 to allow you to see this part. So this is a pretty nice structure, stiff enough to withstand the loading. Okay, so then the next one is the actual force. So let's have a look at the actual force, and then you can click on apply. And so if you have a look at the lateral loading, you can surprised to see, you see the lateral loading is actually that accumulated in here when you subject to the lateral loading that applied by the on the side of the building. And you see this tower actually is responsible for the lateral resistance, and then this part of tower that has a little contribution to the lateral resistance, and then the tower here, the vertical one, and then the only responsible for the vertical loading. So you can see in this structure very clearly the structure has been set up to two parts. One part is vertically, that called vertical system, taking the self-weight or vertical loading layer by layer down to the ground. The other one is the tower we form in here, and then they are responsible to take on the lateral loading. So the two systems work together, can withstand the loading more quite efficiently. So you possibly see in some concrete building, and they're not using the diagonal to build up this one. Instead, they use a shear wall put in the corner of the building to take the lateral loading. That it has a quite efficient system as well. So so this is the actual force. Then you can also have a look at the combined one first. Let's have a look at the combined actual force. So you see this caused by the lateral loading, and this caused by the vertical force, and that's pretty robust structures. So let's have a look at the bending moment. So if you have a look at the bending moment, so this is the vertical system, which it is the I need to untick the actual force. My bending moment apply. So you see that is caused by the UDL. So this is like a simply support beam. So they have the vertical loading, vertical bending moments showing in here. And then the lateral loading they have in this system, they have a very little bending moment inside the structure because of the structure is pretty stiff, and then so they not move too much, and the bending moment inside this one is pretty small, and so that's a combined effect. So looks like quite interesting. And compared to the one we had before, the rigid one, so all the bending moments inside the structure are smaller. So in structural point of view, this structure is more efficient to withstand the lateral loading compared to the one we had before. But however, you do need to put in a diagonal in here, so to form stable structures. So this is the what we have for the second example, and then I hope you enjoy that. Thank you so much. Bye bye.